Okay. Okay. Good afternoon, everyone. Welcome to the seminar today. So the seminar today is organized together with the Biostatistics Department. So today we're very privileged to have invited Professor Jeffrey Rosenthal as our speaker. He is a professor of statistics at the University of Toronto. And in 1992, he received his PhD from Harvard University. And he was awarded numerous prizes. And for example, in 2006, he was awarded the CRM SSC Prize and the COPS President's Award in 2007, which is the most prestigious honor given by the statistical societies. And he has published over 100 research papers and 5 books, among which he wrote a bestseller book for general public, which is named Struck by Lightning, The Curious World of Probabilities. So this book was published in 16 editions and 10 languages. So on his website, he said, despite being born on Friday, the 13th, Rosenthal has been a very fortunate person. Okay, so let's welcome Professor Rosenthal to give us this talk today. Thank you.
Okay, thanks. Hello, everybody. So I have a nice intimate crowd. I guess there was a little confusion about organizing the seminar, so it's just only announced recently. But those who are here, thank you for coming. And I always like on Zoom to see people on the camera. So of course it's up to you, but I think it would work fine if you all want to show your camera and then we can see each other and make it a little bit more of an event. You don't have to, of course, with my students, they have to, but with you it's optional. But I always feel like we have to replace the human interaction as best as we can. I see some people opening up now. Thank you. Nice to see you people. Oh, you all look wonderful. So I feel happier already. Okay, so I'm going to be talking about some work to do with MCMC or Markov chain Monte Carlo algorithm. And first of all, with all the crazy technology, we should see how that's working. So can everybody see my slides now? Yeah, see, I can see you nodding, which I couldn't have seen with your cameras off, but now I can, so that's great. And I'll try to keep it pretty interactive, and I'll use a graphical simulation to try to make it more concrete. So we'll see how we do. So we'll go ahead, and of course, if you ever do have questions, you're always welcome to interrupt, raise your hand or unmute or say something, no problem at all. So so to start off, let's see, there we go. So I'll start with some basic background, which might not be needed for this group, but never hurts. Oops, why is this not running for me? There we go. So so often, the sort of setup for what I want to think about is that we have some complicated high dimensional density function. So I'll usually write it as pi. It's a function on some state space, and density just means some function that's non-negative that integrates to 1. Often that would come from a Bayesian posterior distribution. In fact, Alexandra was just saying it's great to have a Bayesian talk. So this isn't so much a Bayesian talk, but the motivation largely comes from Bayesian because we think, okay, we have this density function pi, maybe it's from a Bayesian posterior, and we'd really like to know what the what we'd like to know things about it. So I would say that we want to compute things, for example, a probability. We want to say, given all these variables in this high dimensional space, and then we have this Bayesian posterior density, which is supposed to tell us the relationship of all these different variables to each other. And now we want to compute a probability. Maybe what's the probability that the first variable is bigger than the second variable, something like that. Or we want to compute an expected value. Maybe h is the sum of the squares of the variables, or a ratio of 2 variables, or whatever. And we want to say, on average, what does it equal? So that's the kind of thing we'd like to compute. And if you're a mathematician, you say, oh, compute an integral. We just use calculus. We know how to do that. Or you say, okay, if it's too hard for calculus, maybe we can do numerical integration. But the point is that typically, pi is, first of all, high dimensional enough that we can't do numerical integration, and also complicated enough that we can't use calculus. So again, I know most of you realize this, but here's a typical example. So I'll just go right down to setting it up. So I'm not going to use this example, so don't worry about this, but it's probably a lot of you have seen this kind of thing before, where this is a very typical example, sometimes called a fixed effects model, or variance components model, or random effects model. And we say, well, we have a bunch of different variables and they all have different relationships to each other in terms of normal distributions and inverse gamma distributions and multiplying them. And it ends up being a few lines of multiplying all these variables in different ways to get some crazy density function. And in one application, in the data, this capital K parameter was 19. So the dimension was 22. So it was like a 22-dimensional function, and it's non-negative function, and it integrates. Well, we have a normalizing constant that should make it integrate to 1. We don't really know anything about it, and I'm sure some of you are using posterior distributions much more complicated than this too. So we say now, oh yeah, sure, you want to find an expected value. Could you integrate this? Well, probably not, right? It's going to be pretty hard. And mathematically speaking, it's well defined what an expected value with respect to pi is, but it's high dimensional, it's complicated. How can we actually compute it? So that's just the motivation that, again, probably you all know, is say, okay, fine. So we have these big complicated densities. We'd like to be able to compute from them. What are we going to do? So the sort of a vanilla Monte Carlo, which again, I'm sure you mostly know, is to say, well, if we could sample from pi, so we could write a computer program that gives a bunch of different samples, and each one might be like a 22-dimensional vector, which has the probabilities which are implied by that crazy density function, and they're independent, identically distributed. Then that means, well, if we could write a computer program to sample a bunch of them, then we say, no problem. Now we can estimate an expected value by just taking an average of the function values over a big sample, right? And this is kind of vanilla Monte Carlo, which probably, again, everybody here already knows. And that's great. But then the question is, how do you write this computer program? You know, we had that crazy posterior distribution. It was 3 lines of products of different density, different variables. Now write a computer program which gives a 22-dimensional vector whose probabilities are generated from that density function. I don't know how to do that. So that seems pretty hard. So instead, we use Markov chain Monte Carlo, which is the topic of this talk. And we say, so what is Markov chain Monte Carlo, or MCMC? And again, probably a lot of you know it, but let's start from the beginning and say we have a complicated high-dimensional target, and we define a Markov chain, which probably you know, and if you don't, it's a sort of a random process or an iterative process that we start with some first variable, which could be a 22-dimensional vector, and then given that, we generate another variable, 22-dimensional vector, and then another one. So we're sequentially, randomly generating these random variables, and we want it such that it converges in distribution to this big complicated thing that we were interested in. And if you have something like that, that means for large enough n, and I put that in quotes because that's a big issue in MCMC that I'll talk a little more about, but for large enough n, the laws or the probabilities of the xn's are approximately from this target distribution. So we had that crazy posterior, which is a product of 3 lines of things or whatever, but no problem. After we run an iterative Markov chain process, that after a while, the probabilities are approximately the probabilities that we want. And then you say, great, so once we get to a large enough n such that we have good probabilities, then you say, no problem, now we're going to just average up the values again, just like before. So this is MCMC in a nutshell. And it's very popular. I probably don't have to convince you that it's used all the time for Bayesian inference. Getting back to Alexandra's comments, this is a Bayesian talk because it's for Bayesian inference, but it's used in computer science, used in finance, physics, engineering. It's used a lot. And in fact, I get questions from all different disciplines. I've recently been working with some engineers who said, hey, you know about MCMC, we really need to use it. So people are using MCMC all the time, right? This basic idea. Now, if you haven't seen it before, but probably you all have seen it before, then you say, how do you make a Markov chain whose probabilities converge to pi? And it's not so obvious if you haven't seen it before. Even if you have seen it before, I think it's kind of amazing. So the most common and the original case is what's called random walk Metropolis algorithm. It goes back to 1953, which is pretty incredible. What is that? That's now 67 years ago, and computers were very primitive, but they were already running MCMC. And I have to tell you the rules for how you iteratively randomly define these x's. And again, you may have seen this all before, but given an xn minus 1, it's a 2-step process. So first you propose a new state from some distribution, which I'll assume is symmetric around x. For example, maybe a normal distribution around x, or we'll have other examples. But we propose some new distribution, and then we either accept or reject it. So with probability alpha, this minimum of 1 and pi of the new state over pi of the old state, we accept it, which means our new state is y. Otherwise, we reject it, and our new state is the same as the old state. So that's it. That's the whole algorithm. So you just propose a state from some simple distribution, like a normal or whatever, and then you either accept or reject it with a certain probability, and that's it. And then that gives you xn, and then you do it again for xn plus 1, xn plus 2, and so on. Each time propose, and then accept or reject. And it's a fact that's not too hard to prove that this rule for the probability of accepting, this alpha, is just right to make this Markov chain be reversible with respect to pi, which means that pi is a stationary distribution. And if you remember your Markov chain theory, it's also going to be aperiodic and almost always going to be irreducible. And then that's what means that X then converges to pi. So even if you didn't know it before, you're now all experts in MCMC. That's really what MCMC is all about. And I want to run a simulation here, so I hope this is going to work. So first of all, can everybody see this display now with a bunch of blue lines and stuff? Yeah, I see some nods. So this is my graphical impression of a Markov chain Monte Carlo algorithm. So what's going to happen, whereas usually the blue bars are going to represent pi, which is usually a big complicated distribution on a high dimensional space, like 22 dimensions, like that crazy product. But for this talk, we're going to keep it simple. It's going to be just a probability distribution on 6 points, 1, 2, 3, 4, 5, 6. And the height of the blue bar is representing the probability there. So this one's about 0.09, that's about 0.13 or 0.16 or so on. They add up to 1. And the black dot is a Markov chain. And the rule is we're going to have a rule. So it started at the state 5. We're going to have a rule for what it does. It's going to run a random walk Metropolis algorithm. And here's what it's going to do. It's going to, oops, there we go. So it's going to do a proposal, which might be from a normal center to 5, but since it's discrete, I'll just do plus or minus 1, the current state plus 1, or the current state plus 2, or the current state minus 1, or the current state minus 2, with probability a quarter each. So very simple proposal. And by the way, the computer is doing this randomly. I don't know how it's going to go, but in this case, it proposed to move from 5 to 6. It chose one of those 4 points. And now it has to accept or reject. So the rule is you look at pi of the new state, which is 6, which is about what, 0.18 or something, divided by pi of the old state, 5, which is about 0.32 or something. So you look at this ratio. So it looks like what maybe 60%. So there's about a 60% chance that we're going to accept it. So this yellow thing is now going to turn green or red if it accepts or doesn't accept. So, okay, it turned green. That means it accepted this proposal. So that means it says, fine, now we're going to move over to 6. So that's what it does. And we've now done one step of the Markov chain, right? I'll do it again. So we again propose plus or minus 1 or 2 from our current state. In this case, okay, it chose to propose to go back to 5. It's a little bit boring, but there you go. And the proposal, well, pi is bigger here, and that means it always accepts it. So I'm sure it's going to accept that state. And it moves back to 5. Does it again? Let's see. Oh, it proposed to move to 7 now. Pi is 0 at 7, so it's always going to reject, I'm sure. So this time it'll turn red. That means it says, forget it, I'll stay at 5. Let's do one more. This time, propose to go back to 6. It's getting a little bit boring, but about a 60% chance of accepting. It accepted again. And let me get that running. So it'll run automatically now. And he's proposing. So far, it's really only gone back and forth to 5 and 6. It's happening randomly. I have no control. Okay, propose to 7. It's not going to do that. Let's do one more, see if it proposes. No, it's still going back and forth. While it's doing that, let me add one more ingredient to my simulation, which are these black bars. And that's what I would call the empirical distribution, which is just checking what fraction of time it's spent so far at all these states. Now, at the moment, it's pretty embarrassing. It's still that way, that it's only been at 5 and 6, right? It's never made it to 1, 2, 3, or 4. So these black bars are really big, and there's no black bars at 1, 2, 3, or 4. But let me run it a little faster, so hopefully we'll get you. There we go. Finally made it to 4 and back to 5. Hopefully it'll, I better run it faster because I have a limited time and I want to show you something good, which takes a while, but eventually, man, it's really, this is the worst beginning of a Markov chain I think I've ever seen. But one way or another, it's proposing and then accepting or rejecting. And you wouldn't really know it so far because so far it's been stuck at 5 and 6 most of the time. But if I run it fast enough, and I see I'm going to have to go faster because I'm not impressing you very much yet, but in the long run, it's going to have probabilities of getting to each of these states, which are given by the height of the blue bars. So what it means is if I run this for a really long time, and the way it's going, it's going to have to be a really long time, go even a little faster, eventually the black bars should approximately converge to the blue bars. So it's, I don't know, I still find it kind of amazing that Markov chains work this way. And from this very simple rule of just propose from a simple distribution and then accept or reject, that's all it takes to say in the long run, the black bars are going to converge to the blue bars. Now, we got off to such a bad start that 5 is still too big and 1 is still too small, but well, it's starting to settle down. So you can see as you run it for a long time, we'll go even faster. Then eventually the black bars converge to the blue bars. So that was an illustration that MCMC doesn't work that great. Even on a simple example, it could take a long time. But nonetheless, it's an illustration of how MCMC works. It proposes and then accepts or rejects in this case. We'll go a little slower. And then And then in the long run, it has probabilities which converge to the target. And so just to be absolutely clear on this, in a typical example, the blue bars would be a high dimensional thing that you can't really understand, you can't integrate, you can't take expected values. But the black dots, that's just the Markov chain. You can keep track of all the samples from the Markov chain, and then you could use them. For example, if you wanted to know what's the probability that, according to the blue bars, that it's more than 3, that is 4 or more, well, you could just count what fraction of the time the black dot has been at 4, 5, and 6, and so on. So that is MCMC in a nutshell, which again, I realize a lot of you probably already knew, but nonetheless, I'll pause just in case anyone has had any questions about that before we continue. Maybe not. At least I can see you. Thank you for that. By the way, I keep looking over and seeing the biggest, brightest smile of all is coming from Nika, but then I realize that's just her photograph. Her camera's off, but that's okay. So the rest of you have nice smiles too. But anyway, so then here, let me first of all zero the count. Let's start over again. Right away, if you should hopefully start thinking of various questions, which is, for example, I made this rule that each time I propose to move either +1, +2, -1, -2, I didn't have to choose that rule. Any rule which is symmetric about the current point would be fine. So right away I could say, you know what, I'm going to do ± 1, 2, or 3. And now I'm going to run it. The same rules as before. It still takes a proposal and then accepts or rejects according to that same rule, looking at pi of the new state over pi of the old state, and has to decide whether it's hopefully in the long run the black bars converge to the blue bars, and if I go a little faster, hopefully we'd start to see that. But right away you can ask which is better. So Markov chain theory says each of these choices, eventually the black bars will converge to the blue bars, but right away we have a choice. And in fact, if you don't mind, maybe to get us all involved, I'll ask you to choose by a show of hands. Suppose you had to pick. We're going to run a Markov chain. You wanted the black bars to converge to the blue bars. You could choose between ± 1 or 2, or ± 1, 2, or 3. Your choice. Who would say I'd prefer the first one, ± 1 or 2? Put up your hand, I can see. Couple who would say, no, I prefer the second one, 1, 2, or 3. Okay, the vote was about 2-2 with 9 abstentions. Okay, well, it's not too bad. Okay, so the point is it's not that clear, right? And you might think, well, if we propose things that are farther away, then it's going to be better. So I can say, well, maybe ± 1, 2, 3, or 4, or ± 1, 2, 3, 4, 5, and so on. But you can quickly see if we take that to extremes, so let's say I do ±, let's go right up to ± 20. And now I start running this. Well, what's going to happen? It's going to propose usually such a big step that it's going to propose to where it's 0. So it's not actually going to work very well. When it finally, here, let me zero the count so we're starting again. When it finally accepts 1, it might move a lot. So that's go there. Well, it only moved 1, but it could move anywhere when it accepts. But most of the time it's going to reject. And not just on this fake example, but on a real example, that would be true too, because if you have some sort of a density, maybe from a Bayesian posterior, well, it might have some tails, but it's pretty much going to go off to 0 in the tails. So you don't want to propose anything too big, or you'll usually reject it. On the other extreme, maybe I'll go back to ± just 1. Then, well, now I'll zero the count again. You're probably going to accept more of your moves, so that's the good part. But on the other, so far you're rejecting a lot. But then on the other hand, you're not going to move very far, and it's going to take a bunch of moves to get, for example, from 6 to 1. So right away we can ask about which MCMC works better or works worse. Okay, so I'll go back to the slides now unless there's any questions about that. Okay, so let's see, here we are back at the slides, so you can still see the slides again now, right? So okay, so the first question, which I already hinted at, is how do we optimize this? That is, what's the best choice? So suppose we're doing a Metropolis algorithm, which is just one kind of MCMC, but even for that kind, we can say, well, what's the optimal choice of the proposal distribution, right? So remember, you had to propose a new state Y, and then you either accept or reject it. And so I already showed you in the JavaScript example that it could be, a good choice could work very well, but a bad choice, like that ± out all the way out to 20, doesn't work so well. So we do care about that a lot. And in a harder, higher dimensional problem, it's actually more important because there's less understanding of what the scale should be and more choices. So, and even often we'll do the proposal will be a normal centered at the current state. But even so, what should that covariance matrix be? And even if it's a multiple of the identity for the covariance, should it be a big multiple, so you're proposing something big, or a small multiple, so you're proposing something small? So yeah, so intuitively, I sort of said this already. As far as the acceptance rate, well, you don't want it to be too close to 0, because if you almost always accept, that's like this plus or minus 1, 2 up to 20. That's not very good. But what's a little bit less intuitive is you probably don't want the acceptance rate to be really close to 1 either, because if it's 1, that means you're almost always accepting your moves, which sounds good, but that probably means you're not taking moves that are very ambitious, right? You're just making little moves and then you're accepting them, but you're not moving very far. So in fact, there's something I like to call the Goldilocks principle. So if you know the story of Goldilocks, she wanted, the porridge shouldn't be too cold and shouldn't be too hot, should be just right. The bed shouldn't be too soft, shouldn't be too hard, should be just right. Well, the Metropolis algorithm, the scaling size shouldn't be too big, shouldn't be too small, just right. And that's just sort of a vague principle, but there's actually some pretty amazing work started by Gareth Roberts and his colleagues about optimizing this using diffusion limits. And they had some quite strong assumptions, which I might say a little more about, but they said under these very strong assumptions, they took a certain limit and they took where the algorithm goes faster and faster, but it takes smaller and smaller steps in higher and higher dimension. And then you look at one component and try to optimize the speed. And when all is said and done, they said under these very strong assumptions, you learn certain things. And one thing you learn is that the optimal acceptance rate, at least under these strong assumptions, not only should it be far from 0 and far from 1, but specifically it should be close to 0.234. And there's actually more that can be said. As long as it's pretty close to 0.234, it's fine. It doesn't have to be exactly 0.234, but that gives you an idea of what you want. Also, and what's a little more relevant for what I'm going to say next, they said, you know what? If you're doing a random walk Metropolis proposal, and if you're going to use a Gaussian, so the proposal is going to be normal, and it's going to be centered on the current state, then here is actually the best choice of that covariance matrix, right? We said this sigma sub p, what should it be? Well, here's what it should be. So the 2.38 as the standard deviation, that just sort of comes out of an optimization, but it should scale like 1 over the dimension. So if you're in higher dimensions, you have to propose smaller things, otherwise you're just going to reject them. But also it should be proportional to the target distribution. So this is, sorry, it should be proportional to the covariance of the target distribution. So pi itself is a big probability distribution on some d-dimensional space. It has an implied covariance matrix in terms of how its different components are related according to pi, and you should do something proportional to that. So in a way, this is a pretty amazing result, or a set of results that they came up with. And one thing is that, well, it's really only proven under these very strong artificial conditions, but like a lot of theory results, to formally prove it, you need these very strong conditions, but in practice, it seems to approximately hold much more widely. So I think this is good advice, and especially the 0.234 actually is pretty good, even for a harder problem. But on the other hand, the second thing, it sounds great. It says, here's how you should do your random walk Metropolis, but there's a problem here that hopefully some of you are seeing already, which is, it says your instructions for how to run your random walk Metropolis algorithm to be optimal, to be the best it can be, is in terms of the covariance of the target distribution. But we already said pi is a big, complicated, high-dimensional distribution that we don't know anything about. How can we possibly know what the covariance of the target is? So that kind of sets up what I want to talk about. So say it again. So we have guidance in terms of these useful things, but we don't know what proposal will lead to a good acceptance rate. You could maybe do that by trial and error. But more importantly, we have no idea how to compute sigma sub t. I mean, it's sort of a chicken and egg, and I sometimes call it the chicken and egg problem, because if we had a really good sample, we could use that to estimate the target covariance, because we know all about the distribution. And if we knew all about the distribution, then we could run a really good Markov chain, because we know how to optimize it. But sort of a chicken and egg thing. So in practice, people do some sort of trial and error where you run the Markov chain, it's not too good, and then you try changing it and try it again and monitor the acceptance rate and do some examination of the output. But another thing you can try to do is let the computer help you as it goes. So you're kind of gradually trying to learn about pi and then use that information to make the Markov chain better, and then use that to run a better Markov chain and learn more about pi. So that's what we call adaptive MCMC. And I'll set it up like this. Suppose we say we have a family of different Markov chains, each of which has the right stationary distribution. So it's like in my example, where we could do just plus or minus 1, or plus or minus 1 or 2, or plus or minus 1, 2, or 3, and so on. So we have a lot of choice. So we have a whole family of things that might work. And then, sorry, how do I wake this up? We let the computer choose as it goes. So we can think that At the nth iteration, the nth time we're running this Markov chain, we choose some p sub gamma n, where gamma n itself is like a random variable choosing among these different possible choices according to some adaptive rules. And again, the logic is pretty straightforward. The logic says the more we learn about pi, the better a Markov chain we can run. And the better a Markov chain we run, the more we can learn about pi. So let's try to do it both ways. And let me again illustrate it graphically. So remember this, let's tell you what, let's zero this, and let's do 1 plus or minus, oops, I didn't mean to do that actually, but let's say we do 1 plus or minus 1, and we do a move, and then we do another one. But now I'm going to change one more thing. I have an adaptive option in this JavaScript thing that I wrote, which says it's going to change its mind about how big a plus or minus proposal to make each time, depending on the previous one. If the previous one was accepted, it'll increase it by 1, because oh, this is pretty easy. I think I can propose something bigger. But if the previous one was rejected, it's going to decrease it by 1. So let's try that out. So the first time it's just doing plus or minus 1. Ooh, it rejected that. It can't go any lower than 1, so that's not a good example. It rejected that one too. I should have planned this better ahead. Okay, it finally accepted one. So now it says, now I've accepted one. So now fine, now I can do plus or minus 2. So I didn't explicitly change to plus or minus 2, but it automatically did. In fact, let me get it running. So I'm not touching anything now. You can see my hands. It rejected that, so it goes back to plus or minus 1. Now it accepted that. Now maybe it'll go to plus or minus 1 or 2, because it can be a little more ambitious. Rejected that one. It's going to go back to just plus or minus 1. Again, we're getting a lot more rejections than usual today. I don't know if it's because it's on Zoom maybe. Now it's plus or minus 1 or 2, so it increases a bit. But accepted that. That's a little better. We're getting the plus or minus 1, 2, or 3 now. And it's gradually getting more ambitious. Oh, we accepted that. This is better now. Now it does a plus or minus 1, 2, 3, or 4. It accepted that. Now it's going to do plus or minus 1, 2, 3, 4, 5. But at some point, it's going to, okay, accepted that too. It's actually a big run, doing plus or minus 1, 2, 3, 4, 5, 6. At some point, it's going to start rejecting because it's getting too big. Now it goes back to 1, 2, 3, 4, 5. Now it rejected again. Goes back to just 1, 2, 3, 4. Accepted that one. It'll go back to 1, 2, 3, 4, 5. And let me run that a little faster for you now. So you can see that it's doing the same algorithm that I showed you at the beginning, but it's saying we don't know which is the best choice, plus or minus 1, plus or minus 1, 2, or whatever. Let's let the computer adjust it as it goes. And it's adjusting as it goes by saying, you know, when I accept a new proposal, okay, maybe this is easy. I can actually propose a little bigger next time. But when it rejects, it says maybe that's getting a little too big. Let's shrink it down by 1, except it never goes below 1, which is the smallest that makes sense. So fair enough. So that's adaptive MCMC in a nutshell. Any questions about that? Everybody at least understands the idea here. It's adapting as it goes, right? Easy enough. Maybe it's too easy. So then you think, okay, well, this is great. You know, and well, let me go back to the slides, because you say, wow, this is great. We don't have to try to figure out, because again, on this simple example, you could just kind of guess, maybe plus or minus 1, 2, or 3. That's maybe the best, or 1, 2, 3, 4 is maybe the best. But on a big, complicated 22-dimensional example, you really have no idea. Should it be, you know, big scale, small scale, whatever. So, okay. So anyway, can this help us find better Markov chains? And I want to show a few examples, say, yes, it definitely can. But then, especially for someone who's more on the theory side like me, you say, but wait a minute, could it, you know, the whole reason MCMC worked is because of Markov chain theory. Now we messed up the Markov chain thing, right? Because Markov chains aren't allowed to change their mind about what to do next based on the history. But that's what we're doing now. We're changing our minds based on the history. So it's not guaranteed to have the right stationary distribution, the right Markov chain convergence properties, and so on. Will it still converge to pi? And I know the answer to that too. The answer is sometimes. So it's a more complicated situation that, that we have to talk about. So in the remaining time, I'll try to talk about each of those things. So the first one is some examples. So here is a 100-dimensional target. So if we're going to do, well, first of all, the target covariance and also the proposal is a 100 by 100 positive definite matrix. So it has over 5,000 entries. And we know that the optimal proposal would be a normal centered at X with this crazy covariance matrix, which depends on this target, right? But we don't know what the target is. So we can use its empirical estimate. So there's sort of two ideas here. One is to say, well, we don't know what the true target covariance is. If we did, we'd use that to try to get a really good Markov chain, but we don't know. But we can estimate it, because if we've run the Markov chain for n steps, we have n vectors, let's say 22-dimensional vector, well, actually in this case, 100-dimensional vectors. And we we have these n different vectors. Well, you can compute, you can do it in R, compute the empirical covariance of these n different 100-dimensional vectors, right? So you can do that, and you can get a 100 by 100 empirical covariance matrix sigma n, and then you could try using that. So instead of doing the normal where it's got the sigma target, you do the normal where it's got a sigma n in it. And you may have noticed I have a small number beta where I put a little bit of a fixed amount in, which is just to avoid traps, and I'll come back to that later. But most of the time, with probability 95% or whatever, we're proposing from a normal, which is just like what the optimal would be, except we don't know sigma t, so we substitute the empirical. And this is essentially the algorithm, which they called adaptive Metropolis, of some Finnish authors, Harjo et al., back in 2001, so it's a while ago. And how does it work? So here is a big blob. And what is this big blob? This big blob is showing the first coordinate of a 100-dimensional Metropolis algorithm that's using this adaptive technique. And on the x-axis is just n, so it starts at x0, x1, x2, and so on, up to 1,000,000, so doing a big run. And on the y-axis, that's just the value of the first coordinate of each of these 100-dimensional vectors as it runs this Markov chain. And at first, it just like is a big blob. We couldn't learn anything from this. But if you look a little more closely, you can see there's some structure here. And in particular, from about here on, about 300,000 or 400,000, which is about here, this is actually a great Markov chain. It's great MCMC. It's converged, it's stationary, it's mixing well, it's giving really good samples from the target distribution. And, as you can kind of see, and anyway, trust me, I've studied this one a lot, I know. But if you look at the first part, it actually looks kind of different. And in fact, for small n, it's really not moving very much, right? It's pretty close to 0. And it gradually loosens up. And then when it gets to about here, then it starts doing really good samples. So what's happening here is it's an adaptive Metropolis algorithm. It's running a really bad Markov chain. It's getting bad samples. It doesn't know what's going on. It's doing a terrible job. And it gradually starts to learn. It says, okay, these are a little bit better samples. Now I can run a better Metropolis algorithm. And then I get some better samples. I run a better Metropolis algorithm. And finally, I've got good samples. I'm running a really good Metropolis algorithm. So it takes a few 100,000 iterations, and it starts working. There's various other ways to study this. One is we define something called the suboptimality factor, which is in terms of the eigenvalues of the optimal Metropolis algorithm, that sort of operator, versus the current version of the Metropolis algorithm. So it's measuring how many times worse is the Markov chain it's running so far compared to what the optimal one would be. And the point is, from about 300,000 on, this is very close to 1, and 1 means it's actually doing the optimal thing. Back here, it's still 50, 100 worse. It's doing a really bad Markov chain. So bad Markov chain becomes good Markov chain. We can go even higher dimensions. This is in 200 dimensions, very similar. Takes just about 1,000,000 iterations to finally figure out what it's doing, and then it runs really well. So you might think, well, gee, that seems a waste running 1,000,000 iterations just to find out what you're doing. But first of all, the computer has to do it, right? We don't have to do it, so that's pretty good. And if you imagine trying to do it, even a 100 by 100 case, you're talking about over 5,000 entries in a covariance matrix. No human could optimize that, no matter how many trials you did and what you tried to do. So we're actually pretty happy that the computer can optimize this for us. So, okay. So what I want to talk about for the last bit of the talk is the issue of, will it still converge? So I sort of hinted at this before. I said, I think this may be my first line here. I said that, it seems to work well in practice, doing this adaptation where you kind of change the rules as you go and learn a smarter way to do Metropolis or to do MCMC. But will it still converge to the pi? That is, will those black bars converge to those blue bars, right? And for ordinary MCMC, it follows from standard Markov chain theory that we've known for well over 100 years. But now we messed it up. We started tweaking based on the past history. And that's where things get more complicated. So I kind of said that here, that ordinary MCMC, if you fix the Markov chain, that's just standard Markov chain theory. Adaptive ones, I said this already, I guess, it destroys that property. There's a couple of things you can do. Now, one thing which I've come to believe a little bit, if you're doing really applied work and you just want to use adaptation and so on, what people often do, and it's probably a good idea, is to do what we sometimes call a finite adaptation, which means you run adaptive MCMC for a while and you do some diagnostics. And actually, I worked with a PhD student to develop some diagnostics. There's an R package with that says, try to figure out when you've done enough adapting. That is, you've been adapting for a while And now you got a pretty good Markov chain, like after you've done, the first 300,000 in that example, or the first million in the second one. Then you say, now we've got a pretty good Markov chain. Now let's stop adapting and use that Markov chain and run regular MCMC. And that's pretty smart, because then the regular MCMC part, you can use standard theory to say it's going to converge. So that may be the smartest thing to do. But what I've worked a lot on as a theory person is, what if you don't do that? First of all, how do you really know when you've done enough adaptation and you want to stop? Maybe you don't know. So maybe you want to keep on adapting. And anyway, suppose you do. Then you say, well, maybe we're going to keep on adapting. And if we keep on adapting, is it still going to converge? And that's where things get kind of interesting. So I want to come one more time back to my 6-dimensional example. And I'm still going to do that same adaptive thing as before. I'm just going to change it a little bit. I just changed the blue bars. So this is a particular example where we still have 6 blue bars, which add up to 1. But it's just a bit tweaked, because now 5 of them, 1, 3, 4, 5, and 6, are all the same value, which is just under 0.02. And the value at 2, you can barely see it. That's not 0, but it's a tiny little value at 2. And now I'm going to run adaptive MCMC. So let me let it run. And you know how this works. Every time it accepts, it's going to increase by 1. So now it'll do plus or minus 1 or 2. Oh, now it rejected. So it'll go back to just plus or minus 1. Oh, rejected that. It can never go below 1. So it's still plus or minus 1. But it's our same trick as before. Now it's going to accept. It's going to do plus or minus 1 or 2 again. Oh, it's going to accept that one too. Now it'll do plus or minus 1, 2, or 3. So far, it looks like it's doing pretty well, and it's kind of the same as before. And there's this kind of gap at 2, but no problem. It could jump over to 1 and then be there for a while, and then it could jump back. Seems like everything's fine. Now it's doing, what is it doing? Plus or minus 1, 2, 3, or 4. But let me run it a little faster, because I know I don't have too much time left. So what will eventually happen, in fact, it already happened. It doesn't always happen this quickly. Maybe all the bad things are happening on Zoom instead of all the good things for the Markov chain. But anyway, what happened actually really fast this time is it was jumping around, no problem, and getting bigger adaptation and so on. Then at some point it jumped to 1, no problem. And then it happened to reject a few. I guess it proposed negative or whatever. And now it's in an awkward place, right? Because it's stuck at 1, and it's proposing plus or minus 1 each time. But when it proposes to 0, it always rejects. And when it proposes to 2, it almost always rejects, because the pi of 2 is so small. And what it means is now, even if I go really fast, so it's doing a warp speed Markov chain, but it's pretty much not going anywhere. And in fact, it will eventually accept it 2, and then it might get out, but it's much harder to get out of this trap, and then much easier to get back into it, because it might just jump to 1 even without going to 2. And in fact, it's not hard to prove that as this pi of 2 actually goes to 0, the limiting probability converges to just a point mass at 1. So even though it's still irreducible and it's still a valid adaptive MCMC scheme, but it's converging to the wrong thing. So, okay. So let me move on from that example and talk a little bit about the theory in the little bit of time I have left. So it does matter, because these simple adaptive rules that you thought were just trying to make it go a little faster, be a little more efficient, are we doing great? It could actually converge to totally the wrong thing, right? And that was an artificial example, but even in a big high dimensional example where it's harder to know what's going on, you could still be converging to entirely the wrong thing, because you're doing adaptation, you're messing with Mr. Markov, right? You're not following the rules for a Markov chain, so you're going to mess it up. So what we'd like to do from a theory point of view is have some simple rules which guarantee that the black bars converge to the blue bars. That is, even though you're adapting, it's still true that if you look at the probabilities for what's happening to the actual Markov chain, they will converge to the probabilities for the target, which was not true in that simple example that I just showed you. So let me, I won't spend a huge amount of time on this. I know it's late on a Friday afternoon, but here's one convergence theorem that goes back a few years now from Gareth Roberts and myself. And it says you will have that property, the black bars will still converge to the blue bars, even though you're messing with it and doing an adaptive version, if you have 2 conditions. The first one we call the diminishing adaptation, and this is actually figured into some other approaches too, where you say, look at how much you adapt between time n, this is the Markov chain you use at time n, and time n plus 1, this is the Markov chain you used at time n plus 1, and say, well, if that is going to 0, so it doesn't mean you have to stop adapting, doesn't mean the total amount of adapting has to be finite, you can keep on adapting forever, but just the amount of adapting you do at any one time is going to 0. And that's not, we don't think of that as such a big deal, because you get to choose the rules for adaptations. We say, fine, just choose the rules to make sure that happens. And that is enough to save you in the example I did with the 6 points, because there There we're changing it by 1 each time. We're not just changing it by less and less each time. So containment is the second of the two conditions. It says the times to stationarity are bounded in probability. So what in the world does that mean? Well, it means if you look at the time from any given point, you're running this crazy adaptive Markov chain, and you're at some state x, and you're using some version of the Markov chain gamma, and then look at how long it would take from that x with that choice of gamma, how long it would take to get within epsilon of stationary. That is for the black bars to converge to the blue bars. So those convergence times, if they remain bounded in probability. So it's kind of a subtle condition, but I think of it as, I think I wrote this next, is avoiding a sort of escape to infinity problem, where the worst thing that can happen with adaptive MCMC is you start off with a bad Markov chain, and that gives you some bad samples. And then those samples make you use a worse Markov chain, and then you get even worse samples, and then you use a worse Markov chain and get worse samples. So it has to sort of prevent you from just sliding off to worse and worse examples, worse and worse Markov chains. And if X and Y are finite or compact, or if their tails are light enough, then we know how to prove it. But in general, it might be hard. So I'll say more about that too. Because anyway, so if you do have those two conditions, then we can prove that those adaptive Metropolis versions are all going to converge to the right thing. We have other versions which are sort of component-wise, just updating one variable at a time. We can prove laws of large numbers. We have results about adapting the coordinate weight. So you might know if you do sort of a random scan where you update different variables with different probabilities. You know, we were working with some statistical geneticists, and they said they have these indicator functions for which of the genes are activated by certain conditions. And we know these ones aren't activated, so we don't want to have to update them all the time. We said, no problem. You can reduce your probabilities of updating those, and you can do that adaptively too. We have a regional adaptive version that we published in JASA a while back about adapting differently for different regions of the space. So generally speaking, you know, I'd say I'm pretty happy with the picture here, except for one thing. And the one thing is what I want to focus the last few minutes on, which is this containment condition, right? So we defined it here. It's a pretty logical condition. It seems to hold in practice, but how do you prove it, right? And so I find myself as a theory person saying, you know, when I'm talking to applied people using MCMC, saying, you know, MCMC is great, and we have these adaptive versions. We think they work well. We want you to use them, but you have to be careful because they could converge to the wrong thing. So you really better use our theory. So you better verify the conditions. But one of the conditions, well, it's probably true, but it's very hard to verify. So just kind of assume it's true, right? But as a theorist, I don't want to have to say that. I want to say, why is it true? So that leads to the last result I'm going to say, and that's why I called this talk Adaptive MCMC for Everyone. They said, well, as long as you have to prove containment and we don't know how, it's not really for everyone because you can't really prove this condition. But what we proved is, first we had some general results about what I called adversarial Markov chains, which is, suppose you have a Markov chain, but there's an adversary who gets to mess up the transitions a little bit on some part of the space. How bad can that make things? And we had certain conditions which would guarantee that it couldn't mess things up too badly. And then we said if we apply that to adaptive MCMC, we say even if the adaptation is messing with the Markov chain a little bit, you'll still guarantee containment and you'll get good convergence if you have certain conditions. So I won't go through these in much detail, but I'll just say they're all conditions which they're a bit clunky, but they're easy to ensure in practice. So one of them is that you have some big upper bound on how big the Markov chain ever moves. So if you're proposing from a normal, there is no upper bound, but if you truncate the normal somewhere, plus or minus 1,000, plus or minus whatever, then you can guarantee that. We say there has to be, if you're way out in the tails, stop adapting. Because if you keep on adapting out in the tails, you could again escape off to infinity or whatever. But if you say adapt any way you want in most of the state space, but just out in the tails, just stop adapting and use a fixed kernel. And then you need some continuity conditions, which are not too hard to ensure. And in fact, that can be relaxed a bit to what we call, we actually now call combo continuous, but you know, sort of more general versions than just continuous. We also have some sort of boundedness in that fixed kernel in the tails, that it's bounded above and below, at least on compact sets. So these are all, we think, fairly mild conditions that you can ensure is true by just designing your Markov chain to make sure. And you know, under continuity, that guarantees that things, you know, things are bounded as long as they're continuous, that kind of thing. And when you put it all together, you say you can ensure these in practice, and then they're enough to guarantee containment. And so that means that applied users can use these things, we think, without needing to worry so much. And that's why we say it's adaptive MCMC for everyone. So, and then, we've applied these ideas to various other things. One recent one was to so-called multiple try MCMC, where if you reject a proposal, you use the fact that you rejected that for your next proposal. Well, we can do that adaptively too, and still assure it's going to converge to the right thing. So that's kind of the state of this adaptive MCMC. So what I'll do now is just summarize a bit, and then I'm happy to take discussion and questions. So to kind of summarize that, I'd say, well, first of all, MCMC is extremely popular in so many fields for estimating expectations. So if you hadn't seen much MCMC before, I hope at least if you got one thing from my talk, it's this is what MCMC is, this is how it works, and this is why it's so useful, because it can be run on all sorts of different target densities, including from Bayesian posteriors, as we were talking about. If you do this so adaptive, which is what I'm kind of focusing on, it says there's all these choices in how to run the MCMC. Let's let the computer help us learn how to do better. Okay, so that's the big idea of adaptive MCMC. It works well in practice. High dimensional examples, adaptive Metropolis, component-wise, probability weights, it works pretty well. It must be done carefully, right? Because we had that simple example with the 6 points. It could get stuck in a trap where it's easier to get in the trap than to get out of the trap because of the adaptive rules we're using. So got to be careful. We have theorems, which say if you have this sort of fundamental property we call diminishing adaptation and this awkward technical property containment, then that's enough to prove it's going to converge. And that can be applied to lots of different contexts. And then we have these adversarial conditions, which provide what we think is a more easy and direct way to verify containment, which is the tricky part of being able to prove that it converges. So, okay. And so at this point, we say, this adaptive stuff is working pretty well, and a lot of people are using MCMC in a lot of ways, but sometimes it's not working as well as it could. We want people to try the adaptation and see how it goes. We want to hear how it's going, and we're happy to talk about that. So that's kind of where things are at. If you do want to know more about the various papers I've written and, well, the Java applets, which are actually now, I wrote Java applets. Now browsers don't support Java applets anymore, so I had to rewrite them in JavaScript, which is what you saw today, and other software and stuff. Everything you want to know about me is on my webpage. I'll put it that way. And with that, I will wrap up. So thanks for listening, and especially thanks for all of you who left your cameras on. It's much better for me when I can see some friendly faces or almost friendly faces. And so I'll stop now and happy to take any questions. So thank you. So if people want to ask any questions, you could raise your hand or just unmute and speak up, or you could type in the chat if you prefer. But if anybody wants to speak up, go ahead. Yeah, go ahead. Abbas. Yeah.
Go ahead.
Oh, sorry, Abbas, and then we'll go to Shireen. So Abbas.
In the normal proposal, if the dimension is large, the sigma n, the empirical sigma could be a bad estimate.
Right. Well, I mean, yeah. So again, yeah. Sorry. Yeah. So as just to clarify, what he's saying, we had this idea that we could do adaptive Metropolis where we don't know the true target covariance, so we approximate it by this empirical one. But you're quite right that in high dimensions, just estimating a big high dimensional true covariance matrix is not easy. Now, of course, as n gets larger, it should get better, right? Because you're getting more and more samples, you're going to get closer and closer to the truth. At least if those are good samples. So maybe let's see. Let me go back to the 200-dimensional example. So oops, too far. So this is a 200-dimensional example, and I mean you're quite right. I mean really the first million iterations here are saying exactly what you said. They're saying, look, sure, if we could understand the 200 by 200 dimensional actionable covariance matrix, if we could approximate that well by the empirical covariance matrix, then we'd run a great Markov chain. But how are we going to do that? That's really hard. And you're right. And the answer is it took about 1 million different samples, which were gradually getting better samples. And then we said, let's estimate the 100 by 100 covariance matrix using 1 million samples. And then finally it works well. So it's a very valid point that it's not going to work so great, at least for small n, might need large n. But as I say, we think, well, it's not too bad because computers are really fast. And remember, we didn't need to do anything. We could take a nap while it worked that out. But you're right, it's a challenge for sure. So.
And one more question.
Okay.
So theoretically, when you say high dimension, do you mean D goes to infinity, or like in your theory, you've fixed the dimension, or
right.
you let it?
So that's a good question too. There's two different parts to, there's two different theory parts. So one is the optimality rules, right? And this is stuff that goes back to Gareth Roberts. And this is actually a theorem as the dimension goes to infinity, and it's sort of a diffusion limit. But then if you go to, for example, our theorems like this one, let's say this is for any fixed dimension, you know, it could be a high dimension, but a fixed dimension, as long as it satisfies certain properties, then it will converge. So the optimality result is really only as dimension goes to infinity, although of course for a large finite D, it's a pretty good approximation. In fact, from simulations, if D is anything bigger than about 10, then it's already pretty good in terms of the optimality. But anyway, as far as the convergence thing, that's not as D goes to infinity. That's for a fixed Markov chain. So
Okay, thanks.
thank you. Okay, let's go to Shireen. Go ahead.
Well, first of all, thank you very much for the very nice talk, and I'm glad this happened with Yi's help. I have a question from an applied perspective that just given the example that you showed us where you had this value in your parameter space that had a high probability and it was kind of separated from the other values with a low or zero probability region, can we generalize this and say that when we have these islands in our parameter space, it's not a good idea to adapt?
Well, I mean, I wouldn't want to say it that way, that it's not a good idea to adapt. What I would say is you better be careful that you satisfy the conditions, right? So I mean, even in this simple example, and I'll say a little more, that the reason this example failed is, first of all, because there was an island, and second of all, because our adaptive rules failed to follow the theory, right? And so in this one, we didn't satisfy what I call the diminishing adaptation, which is that you adapt less as you go. And our theorem would apply. If we did follow the diminishing adaptation, then even if you have islands, it's going to be okay. I mean, this example, it was kind of an artificial example, right? Because it gets into this weird trap where you're at the state one, but you're doing plus or minus one, and then you can't get out of it. I mean, a more realistic example could suffer some of the same thing, where it's sort of easier to get into an island, as you call it, and then once you're there, maybe the rules for the adaptation are such that you tend to get stuck there. So that could happen too. Again, yeah, I guess, as a theorist more, I kind of say, like, it's really hard to say exactly what adaptive rules are going to have what behavior and what applied problems. So that's why we think in terms of, look, what can we prove as a theorem that means it's going to be okay? And we say, look, we got these theorems. If you satisfy these properties, then it'll be okay, whether it's for this simple example or for the harder examples that you're working on. So we kind of say, like, especially in high dimensions, you're not going to be able to check it. I mean, in this case, we can see when it's stuck in a trap, but in your high dimensional problems, you might not know, right? Is it stuck in an island, or is it actually a good sample? So we say, you know, check the theory and get the theory working, and then you should get good samples. That's kind of how we look at it. But.
Thank you.
Okay, thanks. Any other questions? Okay, well, we can leave it there if you want. I know it's late on a Friday afternoon. I know we all have our stresses with teaching on Zoom and all the fun things we're doing, but good to see all you. And again, thank you for having your cameras on. It made all the difference for me, and hope you all have a great weekend.
Jeff, thank you so much for a very interesting talk. It was really nice. So the message is that we have to use MCMC. We have to be careful when using MCMC, right?
Well, that's the meta message. I guess the more specific thing is when using the adaptive MCMC could mess things up, but if you're careful with the theory. So yeah, because I work more on the theory side, our position is this shows why theory is important, because if you start messing with algorithms, you might mess everything up. But if you mess with algorithms, but you also prove some theorems about them, then maybe you don't mess things up. So that's what we say as theorists. But whereas, I mean, just to finish the thing I said about sort of the finite adaptation, where you adapt for a while and then you stop adapting, we did mention that in our original paper as another option, but we were more interested in, how do we prove these theorems? But when I do change hats and say, what about practically using using adaptive MCMC? Well, probably using adaptation to find a good MCMC and then stopping adapting and using regular MCMC with that choice, that may be the best combination from an applied point of view, because then you don't need to worry about these conditions, because MCMC is guaranteed if it's not adaptive. Anyway, I sort of snuck a final answer into what you were just trying to thank me and say goodbye, but I gave one final answer.
No, but it's great, because I really like that paper, and I think it gives you as a practitioner a nice rule of thumb on adapting and making your chains converge faster. So thank you.
Okay, thank you. Okay, all right, thank you all very much. Have a good weekend.
Thank
And
you.
you, bye-bye. Thank you.
Bye.